Did you know the pyramids of Egypt, the Parthenon in Greece, and the towering ziggurats of Mesopotamia all share a hidden secret? They were built with a mastery of geometry so precise, it still leaves modern engineers in awe. Ancient civilizations didn't just stumble upon these breathtaking structures, they wielded geometry like a hidden language, shaping their world with lines, angles, and proportions that defy time. And here's the thing, we're still uncovering the brilliance behind their methods. Imagine standing at the base of the Great Pyramid, gazing up at its perfect symmetry. Every block, every slope, every measurement was calculated with astonishing accuracy, thousands of years before the invention of modern tools. How did they do it? Geometry wasn't just a tool for these ancient builders. It was the heartbeat of their cities, the blueprint of their beliefs, and the key to unlocking the mysteries of the universe. From aligning temples with the stars to designing irrigation systems that fed entire civilizations, geometry was their silent partner in shaping history. Today, we're going on a journey to uncover 35 extraordinary ways ancient people harnessed the power of geometry. You'll discover how they turned simple shapes into feats of engineering, how they encoded sacred knowledge into their architecture, and how their innovations still influence our world today. This isn't just a history lesson, it's a revelation of human ingenuity. So let's step back in time and unravel the geometric secrets that built our past. Trust me, by the end, you'll never look at a straight line the same way again. The Great Pyramid of Giza stands as a testament to one of humanity's oldest geometric obsessions, the pursuit of perfect alignment. Ancient Egyptians didn't just stack stones, they orchestrated a celestial dance with mathematics. Every side of the pyramid points precisely north, south, east, and west, deviating by less than 1/15 of a degree. How did they achieve such accuracy without compasses or satellites? They turned to the stars. By tracking the circular motion of certain constellations around a fixed point in the night sky, Egyptian astronomers could pinpoint true north with astonishing precision. But the genius doesn't stop there. The pyramid's iconic 51.5-degree slope isn't arbitrary, it's a geometric masterpiece. This angle wasn't just structurally sound, it was mathematically sacred. When you divide the pyramid's original height by half its base length, you get a number eerily close to pi, the famous ratio of a circle's circumference to its diameter. Coincidence? Hardly. The Egyptians seemed to encode fundamental constants of the universe into their architecture. Even more intriguing is the pyramid's relationship to the golden ratio, a proportion revered for its aesthetic harmony. The slant height of the pyramid compared to half its base aligns closely with this divine number, found everywhere from seashells to Renaissance paintings. Whether this was intentional or a byproduct of their geometric intuition, we may never know for sure. But one thing's certain, the builders of the pyramids didn't just work with stone. They spoke the silent language of shapes, turning raw geometry into a monument that would whisper its secrets across millennia. While the pyramids reveal Egypt's geometric mastery, another ancient wonder demonstrates how Neolithic builders harnessed geometry to unlock celestial secrets. Stonehenge stands as a silent stone calculator, its massive monoliths arranged with geometric precision to track the movements of the sun and moon. What appears at first glance as a random circle of stones is actually a sophisticated astronomical instrument carved from solid rock. The builders positioned the giant sarsen stones to perfectly frame the summer solstice sunrise when the sun rises directly over the heel stone. Its rays shine through the central archway like a celestial spotlight. But the alignment isn't merely approximate. The geometry extends far beyond basic east-west orientation. Researchers have discovered that certain stone groupings form perfect Pythagorean triangles, those right-angled relationships we learn about in geometry class. These triangles weren't just aesthetic choices, they functioned as prehistoric protractors, allowing Neolithic astronomers to calculate precise angles for tracking solar and lunar cycles. Even more remarkably, the inner bluestone circle aligns with significant lunar events. Every 18.6 years, when the moon reaches its most extreme rising and setting positions, what we call the major lunar standstill, the stones frame these celestial moments with uncanny accuracy. Some archaeologists believe the famous Aubrey holes, those circular pits surrounding Stonehenge, were used like a giant counting device, tracking this 18-year lunar cycle through carefully placed markers. The geometric sophistication extends underground too. Recent ground-penetrating radar has revealed a vast network of geometric earthworks surrounding Stonehenge, forming concentric circles and radiating lines that mirror celestial patterns. These hidden designs suggest the visible stone circle was just the tip of a much larger geometric system, one that transformed the entire landscape into a three-dimensional astronomical model. Whether used for rituals, calendars, or cosmic predictions, Stonehenge proves our ancestors didn't just observe the stars. They measured, calculated, and memorialized them in stone with geometric precision that still challenges our understanding of prehistoric mathematics. The towering ziggurats of Mesopotamia took geometry from the earthly plane to the cosmic realm. These stepped temples weren't just buildings but stairways to the gods, meticulously calculated in shape and angle. Each level of these massive structures formed a perfect square, shrinking precisely as they rose toward the sky. The Babylonians didn't see this as mere architecture. It was sacred geometry made tangible, a physical representation of their belief in a universe governed by mathematical harmony. Take the famous Etemenanke ziggurat in Babylon, believed by some to be the inspiration for the biblical Tower of Babel. Its base measured exactly 180 meters per side, not a random measurement, but one divisible by 60, the foundation of their sexagesimal number system. The angles of ascent weren't left to chance either. Builders maintained a consistent slope of approximately 30 degrees across all tiers, creating a visual rhythm that drew the eye upward while ensuring structural stability. This wasn't just engineering, it was mathematics transformed into spiritual expression. Every staircase winding up the ziggurat's sides carried profound geometric symbolism. Typically built with 7 levels, a sacred number representing the known celestial bodies, the stairs didn't ascend in straight lines. Instead, they spiraled or zigzagged in deliberate patterns, mirroring the apparent wandering motions of planets across the night sky. The number of steps often corresponded to astronomical cycles. Some researchers suggest certain ziggurats encoded the 584-day Venus cycle in their stair counts, turning each climb into a celestial pilgrimage. Even the orientation of these structures revealed geometric intent. Ziggurats aligned their corners with the cardinal directions like Egypt's pyramids, but with an added layer of sophistication. The main staircases frequently faced northeast, not a random choice, but a calculated alignment with the rising of the constellation Draco during important Babylonian festivals. This precision transformed entire cities into giant sundials. During solstices, the ziggurat's shadow would fall along processional avenues at exact angles, marking sacred times in the calendar. The true genius lies in how these temples functioned as three-dimensional diagrams of Mesopotamian cosmology. The square base represented the earth, the ascending levels the 7 heavens, and the summit where priests conducted rituals symbolized the meeting point between the divine and mortal realms. When Babylonian mathematicians developed their advanced understanding of quadratic equations, they weren't just solving abstract problems. They were decoding the geometric language they believed the gods used to shape reality, a language literally built into every tier of their ziggurats. These weren't mere buildings, they were equations in clay and brick, proclaiming humanity's early conviction that the secrets of existence could be measured, calculated, and touched. The Parthenon stands as geometry's greatest illusion, a building that appears perfectly straight to the human eye, yet contains almost no true straight lines at all. The ancient Greeks didn't just use mathematics in their architecture, they weaponized it to play tricks on perception. Every column, every step, every sculpted detail was calculated using the golden ratio, that magical proportion where a line is divided so the longer part relates to the whole exactly as the shorter part relates to the longer. You can see this ratio repeated throughout the temples. Design the width of the columns compared to the spacing between them, the height of the facade relative to its width, even the proportions of individual decorative elements. But here's where it gets fascinating. The Parthenon's architects knew our eyes distort reality when viewing massive structures from certain angles. To counteract this, they employed a series of brilliant geometric adjustments called intosses. The columns bulged slightly outward, not enough to notice at a glance, but just enough to make them appear straight when viewed from below against the bright Athenian sky. The platform itself curves upward in the center by about 7 centimeters, preventing what would otherwise look like a sagging effect to viewers standing at ground level. Even the columns lean inward by 6 centimeters. If you extended them skyward, they'd meet over 2 kilometers above the temple. The pediment sculptures demonstrate even more geometric wizardry. Carved figures at the edges were made disproportionately larger than those in the center. Knowing distance would make them appear equal in size to observers below. The spacing between triglyphs, those grooved rectangular blocks along the frieze, narrows toward the corners in precise increments, creating visual rhythm where none mathematically exists. This wasn't mere decoration, it was a masterclass in applied psychology and geometry. Perhaps most remarkably, these refinements weren't arbitrary. Archaeologists have found numerical patterns in the Parthenon's measurements linking directly to Pythagorean mathematics. The ratio between the temple's length and width echoes the famous 3-4-5 triangle discovered by Pythagoras, while the spacing of columns corresponds to harmonic intervals from Greek music theory. The building literally resonates with mathematical relationships, a physical manifestation of the Greek belief that beauty emerged from numerical harmony. When sunlight strikes those age-worn columns at dawn, what we're really seeing isn't just marble, but stone transformed into frozen music through geometry's invisible hand. Roman engineers transformed geometry into flowing water. When they designed their legendary aqueducts, every curve of those iconic semicircular arches wasn't just beautiful, it was mathematically flawless. To create arches that could support miles of stone while maintaining perfect hydraulic efficiency, they relied on simple compass techniques that would make any modern engineer nod in respect. Starting with a wooden compass wider than a man's arm span, builders would trace 2 intersecting circles into the mortar between stones. Where these circles overlapped created the precise curvature needed to distribute weight evenly across the entire structure. But the real genius lay in how these arches worked together. Roman aqueducts weren't random collections of curves. Each arch's geometry calculated the water channel's ideal downward slope of about 1 foot per mile. This gentle gradient allowed gravity to do its work without causing destructive turbulence. The arches' uniform height maintained consistent water pressure while their spacing followed strict proportional rules. Typically, the height of each arch equaled half its span, creating a ratio that prevented sagging over centuries of use. The water channels themselves reveal even more geometric sophistication. Cross-sections formed a perfect semicircle, not because it looked nice, but because this shape maximized flow while minimizing friction. Hydraulic engineers understood that a semicircular channel with wetted perimeter touching the curve at exactly 60 degrees provided optimal efficiency. They even accounted for seasonal changes. Some aqueducts featured adjustable weirs with movable geometric baffles to regulate flow during dry seasons. Perhaps most remarkably, these constructions weren't just functional. The Romans incorporated golden ratio proportions into their bridge towers and decorative elements, blending utility with aesthetic perfection. When you see those enduring arches marching across European landscapes today, you're not just looking at ancient plumbing, you're seeing geometry made liquid, mathematics turned into life-giving rivers of stone. The Mayans didn't just observe time, they sculpted it with geometry, weaving celestial patterns into a living mathematical tapestry. Their famous 260-day Tzolk'in calendar wasn't simply a way to count days, it was a masterpiece of sacred geometry, where numbers and shapes revealed the hidden order of the cosmos. At its heart lay a complex interlocking grid, 13 numbers paired with 20-day signs, moving in an endless dance like intermeshing gears. This wasn't arbitrary numerology. The 13 represented the layers of heaven in Mayan cosmology, while the 20 corresponded to human fingers and toes, uniting the divine and earthly through geometric harmony. What makes this system truly astonishing is how it mapped onto physical space. Archaeologists have discovered ceremonial platforms with 20 sides, each aligned to a day sign, and staircases with 13 steps representing the numerical cycle. The calendar's geometry extended beyond symbols, it shaped architecture. In the Temple of the Sun at Palenque, shadows cast by precisely angled cornices strike carved markers on specific calendar dates, turning stone into a functioning astronomical clock. The Maya even encoded the calendar's structure into their art. Murals at Bonampak show figures arranged in geometric clusters of 13 and 20, physically manifesting time's architecture. The Tzolk'in's 260-day cycle reveals deeper geometric genius when synchronized with other calendars. When layered with the 365-day Hob calendar, the two systems realign every 52 years, a sacred period called the calendar round. This interval wasn't chosen randomly. It's the smallest number that's divisible by both 13 and 20, while also approximating the average human lifespan in that era. The Maya built entire cities to celebrate this convergence. Circular observatories at Chichen Itza feature 260 markers along their interior, one for each day of the Tzolk'in, aligned so sunlight pierces specific openings on cycle completion dates. But the real geometric marvel emerges when you see how the Maya tracked longer cycles. Their long count calendar employs a base 20 numerical system, Videsimal, with stunning accuracy. They calculated the solar year at 365.242 days, closer to the actual 365.2422 than the Julian calendar Europe was using at the time. This precision came from their understanding of geometric progressions. Surviving codices show they could predict lunar eclipses by modeling celestial movements as overlapping circles with calculated angular relationships. The Dresden Codex, one of only 4 surviving Mayan books, contains pages that function as geometric calculators, grids of numbers that form perfect right triangles when certain cells are connected, allowing priests to project calendar dates centuries into the future. These weren't just tables, they were interactive mathematical diagrams where shape and number merged. Modern scholars have discovered that some temple layouts mirror these codex pages. The buildings themselves are three-dimensional expressions of calendar mathematics, with corridors aligned so sunlight illuminates specific glyphs only on mathematically significant dates. Perhaps most remarkably, the Maya saw time not as a line but as interlocking geometric patterns. Their calendar systems reveal a world view where days weren't simply counted but positioned, each date occupying a specific point in an elaborate cosmic matrix of shapes and angles. When a Mayan priest consulted the stars, he wasn't just reading positions, he was navigating a vast, invisible geometry that connected celestial movements with human destiny through the precise language of mathematics. In the heart of Hindu temple design lies a secret language of shapes where every curve and corner whispers cosmic truths. The ancient Vastu Shastra scriptures didn't just guide builders, they mapped the universe itself onto Earth through intricate geometric patterns called mandalas. Picture this, a grand temple like the Brihadiswara in Thanjavur isn't merely a building. It's a living yantra, a geometric device that channels divine energy through perfectly proportioned squares and circles radiating outward like ripples in a sacred pond. At the core of every Hindu temple lies the Vastu Purusha mandala, a grid of 64 or 81 squares representing the cosmic being's energy field. But here's what's extraordinary: these aren't arbitrary divisions. The central square, the Brahmasthana, symbolizes the navel of the universe, while concentric rings of smaller squares correspond to celestial realms. The outermost layer, 32 deities positioned at precise geometric points, turning the temple floor into a celestial coordinate system. When priests perform rituals at specific intersections, they're not just following tradition, they're activating invisible lines of sacred geometry believed to harmonize earthly and cosmic forces. The genius unfolds in 3 dimensions. Temple towers or shikaras often rise in fractal-like tiers, each level a smaller repetition of the base pattern, creating a visual echo that draws the eye upward toward the infinite. At Khajuraho, the Kandariya Mahadev temple's spire isn't just tall. It's a 3-dimensional rendering of Mount Meru, the axis mundi of Hindu cosmology, with 84 miniature spires arranged in perfect geometric progression. Even the temple's plan mirrors the human form, the sanctum as the head, the halls as limbs, echoing the ancient belief that the microcosm reflects the macrocosm through sacred geometry. Now consider the yantras, those mesmerizing geometric diagrams used in worship. At first glance, they appear as abstract art, but each line holds mathematical precision. The Sri Yantra, for instance, consists of 9 interlocking triangles, 4 pointing upward representing masculine energy, 5 downward for feminine, forming 43 smaller triangles through their intersections. What seems like a simple design actually encodes advanced geometric principles. The angles between triangles approximate 51.8 degrees, the golden angle found in sunflower seed spirals and galactic arms. Temple architects translated these 2-dimensional yantras into 3-dimensional spaces, doorways framed by intersecting triangles, pillars carved with recursive geometric patterns, creating structures where every vista aligns with cosmic proportions. The real magic happens when sunlight enters the equation. At Konark's Sun Temple, the main tower's diamond-shaped carvings aren't merely decorative. They function as a colossal sundial, with shadows tracing specific geometric patterns on the temple floor at solar equinoxes. The entire structure aligns so the rising sun's rays pass through a sequence of precisely angled doorways, illuminating the inner sanctum in a beam of light that traces a perfect golden rectangle across the stone floor. This interplay of light and geometry transforms architecture into a celestial clock, where the sun becomes an actor in a divine geometric play staged in stone. Perhaps most remarkably, these principles weren't static rules but adaptive systems. Regional variations show how core geometric concepts manifested differently across landscapes. Kerala's circular temples embracing fluid curves to harmonize with monsoon winds, while Rajasthan's desert temples used sharper angles to create cooling shaded geometries. Yet all shared one unshakable foundation: the conviction that the universe's deepest truths could be measured, drawn, and stepped into one sacred angle at a time. Deep in the heart of traditional Chinese architecture lies a tool that turns space into sacred geometry, the Luopan compass. This isn't just a navigational device, it's a mathematical blueprint for harmony, with concentric rings of characters and symbols that map cosmic energy onto the land. At its core, the compass reveals how ancient Chinese masters saw the world not as empty space, but as a dynamic grid of invisible forces that could be measured, divided, and balanced through precise geometric principles. The most striking feature is the Bogwa octagon, an 8-sided diagram that overlays the compass like a geometric spiderweb. Each of the 8 sections corresponds to a fundamental life aspect: career, relationships, knowledge. but here's the brilliance: they aren't static categories. The trigram's three-line symbols within each sector form binary sequences representing yin and yang, creating 64 possible hexagrams when combined. This isn't mysticism, it's combinatorial mathematics disguised as cosmology. The octagon's angles aren't arbitrary either. They align with solstice sunrises and sunsets, tying spatial geometry to celestial events. What makes the Liupan revolutionary is how it translates this geometry into practical design. A Feng Shui master would place the compass's center point at a building's heart, then rotate the outer rings until the needle aligned with magnetic north. Suddenly, the Bagua sectors would map onto physical space with mathematical precision. Doorways were positioned along auspicious axes, gardens shaped to balance pentagonal 5-element zones, and roofs angled to deflect negative energy along calculated vectors. The Forbidden City's layout follows this exact principle. Its rectangular walls and gates align with Luosan-derived coordinates, creating what scholars now recognize as a giant energy grid tuned to geometric harmony. The compass's rings hold even deeper geometric secrets. The 24-mountain ring divides the compass into 15-degree sectors, each corresponding to specific celestial mountains in Chinese astrology. This allowed architects to orient buildings so that windows captured beneficial energy from precise angles while deflecting harsh winds along calculated geometric paths. Meanwhile, the 72-dragon ring, a circle subdivided into 5-degree increments, helped determine ideal burial site orientations by analyzing how terrain contours interacted with these invisible directional forces. Perhaps most astonishing is how these principles persist in modern applications. Hong Kong's Bank of China Tower, designed by I.M. Pei, famously applied Feng Shui geometry to its triangular facade. The sharp angles calculated to deflect negative energy while channeling prosperity flows. The building's height, 488 meters, a number derived from compass numerology where 4 represents stability and 8 symbolizes infinity in Chinese culture. From imperial palaces to contemporary skyscrapers, the Liupan proves that ancient geometry wasn't just about measurement. It was a language for negotiating humanity's place between earth and heaven, one perfectly calculated angle at a time. Walking into a centuries-old mosque, your gaze inevitably lifts to the ceiling where a kaleidoscope of stars seems to dance across the tiles in perfect symmetry. These aren't random decorations but masterclasses in mathematical precision, where simple lines and curves explode into infinity through the magic of jiri tiles. Islamic artisans didn't just create art, they engineered visual symphonies using nothing more than a straightedge and compass, unlocking patterns so complex they wouldn't be formally understood by Western mathematicians for another 700 years. At the heart of these designs lies the jiri tile system, a set of 5 polygon templates that function like geometric building blocks. Each tile's shape, decagon, pentagon, diamond, hexagon, and bow tie contains carefully inscribed lines at specific angles. When repeated across a surface, their edges interlock like puzzle pieces, while the internal lines seamlessly connect to form larger, more elaborate patterns. The true genius emerges in how these tiles rotate. Unlike predictable grids, jiri tile layouts follow strict but subtle rotational rules, some turning 36 degrees, others 72, creating intersections that birth 12-pointed stars, swirling hexagons, or endless zigzagging ribbons. What appears as decorative flourishes are actually feats of computational thinking. Take the famous Alhambra mosaics. Every single one of its 17 mathematically distinct wallpaper patterns, a complete classification only proven in the 20th century, can be generated using jiri tile combinations. The artisans worked without algebra or calculus, relying instead on compass and ruler constructions passed down through guilds. They knew, for instance, that drawing a circle, marking 6 equidistant points along its edge, and connecting alternating points would yield a perfect 6-pointed star. But they took this further, nesting smaller stars within larger ones, then repeating the motif across vast surfaces with zero gaps or overlaps. The secret sauce was their understanding of periodic versus aperiodic tiling. Most jiri patterns repeat predictably, but some, like those in Iran's Darb-i-Imam shrine, create quasi-crystal arrangements that never exactly repeat yet maintain perfect symmetry. Modern mathematicians only classified such non-repeating patterns in the 1970s, yet Islamic craftsmen were laying them down in the 15th century. The tile's edge decorations, those delicate floral or calligraphic motifs, they're not mere embellishments but visual cues ensuring craftsmen aligned the underlying geometric grid correctly before adding surface details. Perhaps most astonishing is how these designs encoded spiritual concepts. The infinite repetition symbolized Allah's limitless nature, while the interlaced patterns, where no line ever truly ends, represented the interconnectedness of creation. When sunlight filters through mosque windows, casting moving shadows across these tiles, the geometry seems to breathe, a reminder that even the most rigid mathematical rules can evoke divine transcendence. Across the vast Pacific, Polynesian navigators didn't just sail, they read the ocean like a geometric map, using wave patterns as their coordinates, their secret. Stick charts, deceptively simple arrangements of palm ribs and shells that encoded the sea's hidden mathematics. These weren't physical maps in our modern sense, but three-dimensional wave models where every curve and intersection held life or death navigational data. Shells marked islands, while bent palm ribs represented ocean swells refracting around landmasses at precise angles, an entire seascape reduced to its geometric essence. The genius lies in how these charts translated fluid motion into fixed relationships. Master navigators recognized that waves refracting around an island create distinctive angular patterns like light bending through a prism. A 30-degree change in swell direction might indicate land 40 miles downwind, while intersecting wave trains formed predictable nodes sailors could follow like watery highways. The charts captured these relationships through carefully measured stick arrangements. Diagonal crosspieces might show how a north swell splits around an atoll, creating secondary swells at 120-degree angles, information as reliable as any GPS coordinate to trained eyes. What seems abstract becomes concrete when you're in a canoe. Imagine holding a chart called a matang, its radial sticks fanning out like spokes from a central shell. Each spoke represents not just direction, but the specific feeling of particular wave intervals against the hull. The length between sticks encodes wave frequency. 8 palm widths might equal 8 wave crests per hour, while curvature indicates how swells bend around distant islands. Navigators memorized these geometric relationships through touch, running fingers along the sticks to internalize angles that would later help them correct course by feeling wave impacts shift beneath their vessel. The Rebelib charts took this further, large latticeworks mapping entire archipelagos through interconnected angular relationships. Here's where the geometry gets stunning. Islands weren't placed by physical distance but by their wave refraction signatures. Two atolls might appear close together on the chart not because they're geographically near, but because their swell patterns interact mathematically. A chain of shells connected by gently curving sticks could indicate islands aligned to create a wave shadow corridor, a navigable path where interfering swells cancel each other out at precise 30-degree increments. Modern oceanographers have confirmed the astonishing accuracy of this system. Using spectral analysis, they've found that Polynesian wave interpretations correspond to real oceanographic phenomena, like how the interaction between equatorial currents and trade wind swells creates stable angular wave patterns at 108-degree intervals. These aren't vague observations but reproducible geometric relationships. When NASA studied Marshallese charts in the 1990s, they discovered the stick angles often match the exact degrees at which waves diffract around obstacles according to fluid dynamics equations, knowledge Western science formalized only centuries later. Perhaps most remarkably, these charts weren't static references but dynamic calculators. Navigators would adjust them mentally as conditions changed. If currents strengthened, they'd imagine the sticks bending further, recalculating angles accordingly. This living geometry transformed the open ocean from trackless wilderness into a grid of intersecting lines and angles, where every swell became a signpost and every island revealed itself through the precise mathematics of disturbed water. The stick charts didn't just map space, they revealed the ocean's hidden geometric soul, written in waves and decoded through palm ribs. Ancient Egyptian scribes didn't just write, they sculpted language with ruler-straight precision, turning hieroglyphs into a visual symphony of calculated proportions. Behind every elegant ibis or coiled serpent carved into temple walls lay an invisible geometric grid, a hidden scaffolding that ensured each symbol maintained perfect consistency across generations of artisans. These weren't freehand sketches but mathematical constructions, their beauty born from strict adherence to modular systems that would make any modern typographer nod in admiration. The system was deceptively simple yet ingenious. Scribes worked on surfaces pre-marked with faint squared grids, each box measuring about 1 finger's width, what we'd call a standardized module today. Every hieroglyph had to fit within an exact number of these squares, whether 2 squares tall for a simple glyph like the reed character or 18 squares for elaborate symbols like the ankh. But here's where the geometry gets fascinating. Proportional rules governed not just size but relationships between elements. The owl glyph's round eye always occupied 1/9 of its total height, while the curve of a vulture's wing followed an arc drawn from the corner of its grid square. Even spacing obeyed mathematical rigor. Vertical signs stood exactly 1 grid unit apart, creating rhythmic negative space that made inscriptions visually harmonious. Archaeologists have discovered papyrus sketchbooks where master scribes practiced these geometric principles. One particularly revealing example shows a human figure broken down into 18 equal grid units from hairline to soles, with strict proportional rules. The navel falls at the 11th unit, the knees at the 6th, and the shoulders span exactly 5 units wide. This same grid logic applied to hieroglyphs, whether depicting gods, animals, or objects. The walking legs symbol always showed the forward leg bent at a 45-degree angle from an imaginary diagonal crossing its grid square, while hawk-headed deities had beaks precisely 1/3 the length of their face. What seems like artistic convention was actually profound symbolic mathematics. Certain glyphs incorporated sacred ratios. The jed, pillar of stability, often measured 4 units tall by 3 wide, echoing the Pythagorean 3-4-5 triangle revered in Egyptian architecture. Other symbols encoded cosmological numbers. The star hieroglyph frequently appeared in groupings of 5 points, reflecting their 5-part understanding of the universe. Even the grid squares themselves held meaning. Temple inscriptions sometimes used larger modules for royal cartouches, visually emphasizing pharaoh's divine status through proportional hierarchy. The system's brilliance shines in its flexibility. While the grid enforced consistency, skilled scribes could scale compositions effortlessly simply by changing the physical size of their squares while maintaining the same modular counts. A wall inscription might use 1 centimeter grid units while a tiny amulet employed 0.5 millimeter squares, yet both retained identical proportions. This geometric rigor allowed hieroglyphs to maintain legibility whether carved colossal on obelisks or inked minutely on papyrus, their forms instantly recognizable across 3,000 years of use. When modern designers speak of responsive design, they're echoing principles these ancient scribes mastered. That true visual harmony comes not from fixed dimensions, but from unshakable proportional relationships. Perhaps most remarkably, these geometric rules transcended mere practicality. The grid system mirrored the Egyptians' worldview, just as their gods brought order from chaos through measurement, as personified by the goddess Mat with her measuring rod. Scribes imposed geometric order on the fluidity of language. Each perfectly proportioned hieroglyph wasn't just a letter, but a tiny temple, a sacred space where mathematics and meaning converged. High on a hillside in Greece, the Theatre of Epidaurus performs an acoustic miracle to this day. A whispered word from the stage carries effortlessly to the farthest spectator, nearly 60 meters away. This isn't just clever architecture, it's geometry transformed into sound. The secret lies in the perfect semicircular design, where every limestone seat forms part of an enormous sound-focusing dish. Greek architects didn't guess at these proportions, they calculated them. The theater's 55 rows of seats follow precise mathematical intervals, with the lower 34 rows divided from the upper 21 by a circular walkway exactly halfway up the slope. This division creates two harmonic arcs that reflect sound waves in complementary patterns, preventing echoes while amplifying clarity. The genius emerges in the angles. Each row of seats rises at a carefully calibrated incline about 26 degrees at the bottom, increasing subtly to 30 degrees higher up. This gradient ensures sound waves strike each seat at optimal angles, bouncing upward rather than dissipating sideways. Even the spacing between seats follows acoustic geometry, approximately 60 centimeters apart, a distance that corresponds to the wavelength range of human speech. When actors project from the circular orchestra floor, their voices encounter a series of calculated surfaces. The stone benches act like acoustic filters, absorbing lower frequencies that cause muddiness while reflecting crisp midtones. Modern researchers have discovered astonishing precision in these designs. The theater's diameter relates to its height in a 1:2 ratio, the same proportion found in vibrating strings that produce perfect octaves in music. This harmonic relationship means the entire structure resonates like a giant musical instrument. Footsteps on the stage stones produce tones at frequencies that travel furthest in the space, while the semicircular back wall behind the actors creates a natural soundboard, projecting voices forward with startling precision. But perhaps the most brilliant geometric feature is the buried hollow jars discovered beneath the seats. These weren't decorative, they functioned as Helmholtz resonators, ancient sound amplifiers tuned to specific frequencies. Arranged in carefully spaced grids, their openings face the audience at angles calculated to reinforce vocal frequencies while dampening wind noise. Each jar's volume and neck length corresponded to mathematical ratios from Greek music theory, creating a distributed network of acoustic enhancers. On quiet nights, actors report feeling their voices lifted by the architecture, as if the very stones conspire to carry their words across centuries. What seems like magic is pure geometry in action. From the precise curve of the seating to the strategic placement of reflective surfaces, every element works together to turn whispers into declarations. This isn't just a theater, it's a 2,000-year-old sound system proving that when mathematics shapes space, even the softest human voice can conquer distance. Run your fingers along the intricate curves of a Celtic knot, and you're tracing a path older than written history, a labyrinth of sacred geometry where no line truly begins or ends. These mesmerizing patterns adorning ancient stone crosses and illuminated manuscripts aren't mere decoration, they're mathematical manifestos. Each twist and turn follows rigid geometric laws perfected by Celtic artisans over centuries. The secret lies in their foundational grid, an invisible lattice of equidistant dots that served as the blueprint for every looping strand. Artisans would connect these points with continuous lines at strict 90-degree angles, creating the illusion of infinite threads weaving under and over one another in perfect balance. What makes these knots transcendent is their spiritual geometry. The most sacred designs incorporate three interwoven strands, a representation of the Celtic triple goddess, the Christian Trinity, or the three realms of earth, sea, and sky. When these strands form an unbroken path, they symbolize the eternal cycle of life, death, and rebirth. The Book of Kells reveals astonishing precision in this regard. analysis shows its knotwork maintains consistent strand widths within millimeter tolerances across entire pages, with crossings occurring at mathematically perfect intervals. Some complex knots even encode the golden ratio when you measure the length of a strand between crossings against its width. They often relate by that magical 1/618 proportion found throughout nature. The deeper symbolism unfolds in the negative spaces. The empty areas framed by interlacing strands aren't accidental. They form their own sacred shapes. Pentagrams emerge between the threads of certain Welsh border knots, possibly representing the 5 elements. In some Norse-Celtic hybrids, the voids create 12-pointed star patterns aligning with lunar cycles. Even the number of crossings holds meaning. 7 intersections might reference the classical planets, while 9 could mirror the months of human gestation in Celtic lunar calendars. Modern mathematicians have uncovered even more brilliance in these designs. Certain knotwork panels from the 8th century anticipate mathematical concepts like Borromean rings interlocked circles, where removing any one causes the others to separate centuries before they were formally described. The famous carpet page from the Lindisfarne Gospels contains knot sequences that function as geometric proofs, demonstrating how parallel lines can create optical illusions of depth through calculated spacing. And here's the startling part. Some knots are actually topological impossibilities, visual paradoxes where strands appear to pass through themselves in ways that defy three-dimensional logic, predating Escher's impossible constructions by 1,000 years. Perhaps most profoundly, these knots embody the Celtic worldview, a universe where all things connect through invisible threads of meaning. When a monk painstakingly inked these patterns by candlelight, he wasn't just drawing. He was mapping the cosmos as his people understood it, endless, interconnected, and bound by geometric laws as constant as the turning stars. The next time you see a Celtic knot, look closer. Those aren't just lines, they're the ancient language of eternity, written in the silent poetry of angles and curves. Rising like geometric sentinels above the scorching Persian deserts, wind towers, or badgers transformed arid air into cool breezes through nothing more than sheer mathematical ingenuity. These hexagonal and octagonal towers weren't just architectural flourishes. They were precision-engineered climate systems where every angle served a calculated purpose. The most effective designs employed 8 sides rather than 6, a critical geometric choice that allowed wind to strike at least one face perpendicularly regardless of shifting wind directions. But here's the brilliance. Each interior shaft was meticulously angled to create a venturi effect. As hot wind entered the tower's upper openings, the carefully tapered passageways forced air to accelerate, lowering its pressure and temperature before funneling it downward into living spaces below. The tower's cross-sections reveal even more geometric mastery. Many featured interior partitions forming smaller parallel shafts, some carrying cool air down while others vented warm air upward in a continuous convection loop. The partitions weren't arbitrarily placed. Their spacing followed harmonic ratios found in Persian mathematics, typically dividing the tower's diameter into sevenths or ninths. This created optimal surface area for heat exchange while maintaining laminar airflow. Some towers in Yazd incorporate spiral staircases winding around the central shaft, not just for access, but to impart a gentle rotation to descending air that improved mixing and cooling efficiency by approximately 20% compared to straight designs. The real magic happens at the tower's base, where geometry meets hydrology. Many wind towers cap their shafts above underground qanats, those ancient water channels, so descending air passes over moist clay surfaces or water pools. The octagonal shape proves perfect here too. Its angles create 8 triangular evaporation zones where surface area is maximized without stagnant corners. Architects often added geometric baffles, wooden lattice screens with precisely spaced diamond or hexagon patterns. That further cooled air by breaking it into smaller turbulent streams while filtering dust. Modern computational fluid dynamics studies show these screens could reduce incoming air temperature by up to 12 degrees Celsius through geometry alone. Perhaps most remarkably, some towers integrated celestial geometry. In the desert city of Bam, certain badgers align their primary shafts with summer solstice sunrise angles. This seasonal adjustment ensures maximum airflow during the hottest months, while minimizing winter drafts, all calculated using the same astronomical tables that guided Persian navigators. The tower's heights weren't arbitrary either. They followed proportional rules where height-to-width ratios matched local wind gradient profiles. A 30-meter tower in Kerman, for instance, precisely intercepts the altitude where prevailing winds shift direction during afternoon temperature inversions, a phenomenon Persian engineers quantified centuries before modern meteorology. These structures weren't isolated feats but nodes in larger geometric networks. In the ancient city of Kashan, entire neighborhoods were arranged so wind towers created pressure differentials between streets, cool air flowing inward through some homes while warm air exhausted through others in a city-wide ventilation system. The towers' silhouettes even served as navigational aids, their distinctive octagonal profiles visible for miles across flat deserts, guiding caravans like geometric lighthouses. When you stand beneath one today, feeling that inexplicably cool breeze in 100-degree heat, you're not just experiencing architecture, you're witnessing geometry harnessed as a life-giving force, where every angle and ratio whispers the Persian genius for turning air into art through mathematics. Beneath the vast skies of the Great Plains, the Native American tipi stands as a geometric marvel, a perfect marriage of mathematical precision and spiritual symbolism. That iconic conical shape isn't just visually striking, it's engineered to withstand howling winds and heavy snow through calculated angles. The ideal slope, about 60 degrees at the base, creates a self-supporting structure where gravity pulls the outer cover taut against the poles, distributing stress evenly in all directions. But the genius lies in the tripod foundation. The initial 3 poles form a stable triangular base, locked together at precisely measured intervals that determine the entire tipi's proportions. Subsequent poles follow a radial symmetry, each placed at consistent angular increments that maintain perfect balance whether the structure spans 12 feet or 20. The circle emerges as sacred geometry in every aspect of tipi design. From above, the footprint forms a perfect ring representing the cyclic nature of life, a concept echoed in the hoop dance and other tribal traditions. Even the interior layout follows circular logic. Sleeping areas radiate outward like spokes from the central fire, which itself sits at the exact geometric center. This wasn't merely practical, it reflected the Lakota belief in the sacred hoop, where all directions and elements exist in harmonious relationship. Some tribes incorporated the circle's mathematical perfection into the tipi's very construction. The Blackfoot people, for instance, traditionally used 21 poles, a number divisible by 3 symbolizing sky, earth, and water, and 7 the sacred directions, north, south, east, west, above, below, and within. The tipi's geometry also served as a celestial calculator. The smoke flaps at the top, often adjustable with precisely angled poles, functioned like a rudimentary sextant. Certain tribes aligned their tipis so the summer solstice sunrise would strike specific painted symbols on the liner, turning the entire structure into a seasonal calendar. The Oglala Lakota took this further, designing tipi covers with geometric patterns that, when illuminated by sunlight through the smoke hole, projected moving symbols onto the interior that tracked lunar cycles. Perhaps most remarkably, tipi mathematics extended beyond single dwellings to entire village layouts. When the Cheyenne arranged their tipis in camp circles, the spacing between lodges followed strict proportional rules, often based on multiples of the tipi's diameter, creating defensive sightlines while maintaining sacred geometric relationships between families. The Comanche engineered portable villages where tipis could be rapidly erected in mathematically perfect constellations, their positions mirroring star patterns used for navigation. These weren't just shelters, they were three-dimensional expressions of indigenous cosmology, where every slope and circumference whispered of a universe bound by invisible geometric laws. The next time you see a tipi silhouette against the horizon, recognize it as more than a simple dwelling. Those converging poles trace the path of ancestral wisdom, a geometry that balanced earthly needs with celestial truths, proving that even a nomadic home could hold the precise angles of the infinite. Buried in ancient Chinese legends lies a 3x3 grid so powerful, emperors consulted it like a celestial blueprint, the Lo Shu magic square. At first glance, its arrangement of dots seems simple, 15 dots total, with 5 always at the center, and the numbers 1 through 9 arranged so every row, column, and diagonal sums to 15. But this was far more than a mathematical curiosity. The square's geometry encoded a cosmic operating system, where odd numbers formed a perfect cross symbolizing the 4 cardinal directions, while even numbers occupied the corners representing the earthly elements. Every intersection held meaning. The central 5 embodied the emperor's divine mandate to balance heaven and earth through precise governance. The square's influence stretched far beyond numerology. Imperial city planners used it as a geometric template, designing capitals like Chang'an modern Xi'an as gigantic 3x3 grids. The emperor's palace always occupied the central 5th sector, mirroring the magic square's pivotal 5, while government offices, markets, and temples filled the remaining 8 sections according to their symbolic correspondences. Streets ran straight as ruled lines between these zones, creating urban landscapes where geometry enforced social order. Even today, Beijing's Forbidden City echoes this design. Its 9,999 rooms, one shy of the mythical 10,000 of heaven, arranged in nested magic square patterns that visitors unknowingly walk through like pieces on a living game board. Philosophers saw deeper geometry in the Lo Shu's movements. By rotating the square's numbers in specific sequences, scholars demonstrated the cyclical nature of time, the way seasons flow into one another yet always return to balance. The square's patterns became the foundation of I Ching hexagram transformations, where broken and solid lines shift according to the same mathematical rules. Feng Shui masters still use these rotations today, analyzing buildings by superimposing the magic squares grid over floor plans to identify auspicious angles for doorways and beds. What makes the Lo Shu truly revolutionary is how it blended math with metaphysics. The square's constant sum of 15 wasn't arbitrary. It matched the 15 days between new and full moons, linking its geometry to lunar cycles. Certain configurations revealed hidden symmetries. Drawing lines between sequential numbers created spirals matching the golden ratio, while the square's eigenvalues, a concept not formally discovered until the 18th century, correspond to energy flow patterns in traditional Chinese medicine. Even the dots themselves held geometric secrets when connected. They form perfect right triangles whose angles mirror the inclinations of ancient Chinese sundials. Perhaps most remarkably, the Lo Shu transcended paper. During the Song dynasty, engineers designed water clocks where floating indicators moved through 9 chambers arranged as the magic square, their mechanical movements mirroring numerical sequences. Military strategists deployed troops in Lo Shu formations, believing the geometric arrangement multiplied their effectiveness. And when the square appeared on turtle shells, as legend says it first did, its pattern of dots aligned with the hexagonal plates of the turtle's carapace, suggesting nature itself endorsed this divine mathematics. The next time you see a simple 3x3 grid, look closer. Those aren't just numbers, they're the ghostly fingerprints of an ancient civilization that saw the universe's secrets written in perfect geometric harmony. The Roman road network didn't just connect an empire, it conquered distance itself through geometry's unyielding logic. At the heart of this engineering marvel stood the Groma, a deceptively simple surveying tool that turned landscapes into mathematical diagrams. Picture a wooden cross with weighted plumb lines suspended from each arm, rotating atop a tall staff. When planted in the ground, those perfectly vertical lines became living graph paper, allowing surveyors to project straight lines across miles of uneven terrain with astonishing precision. The tool's genius lay in its geometric purity. By sighting along perpendicular lines simultaneously, engineers could maintain dead-straight alignments even when winding around obstacles. Military campaigns depended on this exactness. A legion marching 30 miles per day needed to know every 1,000 paces. 1 Roman mile brought them closer to their objective. Surveyors used the groma to place mile markers with geometric rigor, not just measuring distance but calculating strategic advantages. On the famed Via Appia, these markers weren't simple posts but miniature mathematical stations. The distance between them often adjusted by fractions to account for elevation changes, ensuring commanders knew true marching times rather than raw distance. The roads themselves were geometric artworks in stone. Their cambered surfaces followed precise parabolic curves, rising gently to a central crest with just enough slope to shed rainwater while maintaining optimal troop movement efficiency, typically a 1 in 20 gradient. Ditches flanking the roads weren't dug randomly. Their depth and angle followed standardized geometric proportions to maximize drainage while minimizing erosion. Even the famed Roman road layers, from foundational stones to smooth top surfaces, followed Fibonacci-like thickness ratios that distributed weight mathematically across the empire's varied terrains. What truly astonishes is how these roads functioned as a distributed navigation system. The consistent angle between milestone placement and roadside shrines created predictable sightlines. A soldier could stand at one marker and visually confirm the next 3 ahead, even in fog or rain. At intersections, carefully calculated turning radii allowed supply carts to pivot without breaking formation, their wheelbases matching the curve's geometry. Modern laser surveys reveal some stretches maintained straightness within 2 centimeters per kilometer, a tolerance that would impress today's highway engineers. Perhaps most strategically brilliant was the network's radial symmetry. All major roads emanated from Rome like spokes on a wheel, but this wasn't just symbolic. The geometric arrangement meant reinforcements could deploy from the capital along the most mathematically efficient paths, a lesson in topology applied centuries before the concept had a name. When Hannibal crossed the Alps with his elephants, it wasn't brute strength that allowed Rome to counterattack. It was the ability to rush legions down these geometrically perfected highways faster than anyone thought possible. The roads didn't just transport soldiers, they multiplied Rome's military reach through the silent power of angles and alignments. Standing like celestial needles across Egypt's landscape, obelisks did far more than commemorate pharaohs. They transformed sunlight into a precision timekeeping system. These towering monoliths, some reaching over 30 meters high, were essentially colossal sundials with a geometric twist. The key to their accuracy lay in the careful alignment between the obelisk's shadow and meticulously placed ground markers. At dawn, the shadow stretched westward as a long, tapering finger, while at midday it shrank to a neat pool at the base. But here's where the trigonometry comes alive. Egyptian astronomers marked the ground with semicircular stone pavements divided into 12 equal sectors, each representing an hour of daylight. As the sun moved, the shadow's tip would travel along these calibrated curves with mathematical precision. The system relied on 2 brilliant geometric insights. First, the obelisk's height-to-base ratio wasn't arbitrary. It was calculated to ensure the shadow's length changed at a consistent rate throughout the day. A shorter obelisk would produce shadows too similar in length between morning and afternoon, while an excessively tall one would cast impractical, sprawling shadows at low sun angles. Second, the ground markings accounted for seasonal variations. Winter shadows followed different arcs than summer ones due to the sun's changing elevation. so pavements often featured multiple concentric rings corresponding to solstices and equinoxes. Priests could track not just hours but the solar year itself by observing which ring the shadow touched. Modern analysis reveals astonishing sophistication in their calculations. The famous Cleopatra's Needle in Heliopolis, now in London, demonstrates this perfectly. Its shadow moves exactly 15 degrees per hour, matching Earth's rotational speed. This wasn't coincidental. Egyptian mathematicians understood that dividing a circle's 360 degrees by 24 hours yielded this precise angular rate. They even compensated for atmospheric refraction, the bending of sunlight near the horizon, by slightly offsetting morning and evening markings. At Karnak, archaeologists have discovered obelisk bases with grooves carved at specific angles to amplify shadow contrast during critical solar events, acting like ancient contrast filters. The real stroke of genius was how they adapted these principles across latitudes. An obelisk in Aswan near the Tropic of Cancer functioned differently than one in Alexandria. Near the tropics, midday shadows sometimes pointed south instead of north during summer months. Egyptian engineers adjusted ground markers accordingly, proving they grasped spherical geometry concepts we now associate with Renaissance astronomers. During the annual zenith passage, when the sun stood directly overhead at noon, certain southern obelisks would briefly cast no shadow at all, a celestial event marked with gold-leafed summit decorations that flashed like beacons when illuminated vertically. Today, we can still witness this ancient timekeeping in action. The unfinished obelisk in Aswan's quarries, had it been erected, would have tracked solstices with its shadow precisely intersecting carved hieroglyphs at the base reading, "The sun is united with the horizon." This wasn't poetry, it was rigorous celestial mechanics where granite became the hand of a cosmic clock, and every shadow's edge whispered the exact angle of Earth's tilt to those who understood its geometric language. Diving into the stormy depths off the Greek island of Antikythera in 1901, sponge divers stumbled upon a corroded bronze artifact that would rewrite history. What initially appeared as a lump of oxidized metal revealed itself as the Antikythera mechanism, an intricate clockwork device with over 30 precisely interlocking gears dating back to the 1st century BC. This wasn't just an ancient oddity, it was the world's first known analog computer, using geometric gear ratios to model the cosmos with staggering accuracy. The largest gear, the drive wheel, with 223 teeth, engaged with other toothed wheels in calculated relationships that mirrored celestial movements. The brilliance lies in how these gears formed a mechanical representation of astronomical cycles. A pin and slot mechanism connecting two gears ingeniously simulated the elliptical orbit of the Moon, accounting for its varying speed as described by Kepler's laws 2,000 years before Kepler was born. Another gear train calculated the 4-year cycle of Greek athletic games, while concentric dials tracked the 19-year Metonic cycle, when lunar phases repeat on the same calendar dates, and the 76-year Callipic cycle, refining lunar calculations further. Modern X-ray scans reveal even more geometric sophistication. The mechanism employed differential gearing, a technology previously believed invented in the 16th century, where the rotation of two input gears produced an output representing their combined motion. This allowed it to display the Moon's phase by subtracting the Sun's position from the Moon's. The gear's tooth counts weren't arbitrary, they embodied precise mathematical ratios. For instance, 127 teeth on a critical lunar gear reflected the ancient Babylonian discovery that 254 lunar cycles approximate 19 solar years, a ratio modern astronomy confirms as 127 to 2,451. Perhaps most breathtaking is how the mechanism's front face displayed its cosmic calculations. A rotating zodiac dial, marked with degree gradations accurate to within half a degree, showed planetary positions against fixed stars. Pointer needles moved along spiral grooves mathematically spaced to represent the uneven duration of seasons caused by Earth's elliptical orbit. Even eclipse predictions incorporated geometric patterns. Inscriptions described upcoming eclipses in 8-color Saros cycles, accounting for both lunar and solar events. This bronze wonder didn't merely predict celestial events, it embodied the Greek belief in a geometrically ordered universe. When you turn its reconstruction's handle today, you're not just moving gears. You're spinning a model of the cosmos as the ancients saw it, a perfect machine of interlocking circles and ratios where mathematics and divinity converged in bronze. Buried in the clay soil of ancient Mesopotamia lies a cracked tablet that appends everything we thought we knew about the birth of trigonometry. Plimpton 322, a palm-sized clay fragment dating back to 1800 BC, isn't just a list of numbers, it's a Babylonian masterclass in applied geometry, revealing how scribes solved complex construction problems 3,000 years before Pythagoras. The tablet's 4 columns of cuneiform numbers form 15 perfect right triangles, each with whole number sides that obey the Pythagorean theorem. But here's what makes it revolutionary: these weren't random examples. They're arranged in descending order of a specific geometric ratio, creating what scholars now recognize as the world's first trigonometric table, not for measuring angles like we do today, but for calculating structural stability in towering ziggurats and irrigation systems. Decoding the tablet reveals astonishing mathematical sophistication. Each row represents a right triangle with sides scaled to eliminate fractions, a clever workaround for Babylonians' base 60 number system. The second column lists the square of a triangle's short side divided by its hypotenuse squared, producing values that decrease with perfect consistency from near 1 down to about 0.4. This wasn't accidental, it demonstrates an intentional study of how right triangle proportions change as their angles steepen or flatten. Modern researchers have discovered these values correspond to what we'd now call the secant squared function, a trigonometric relationship not formally defined until the 17th century. The tablet's practical applications were groundbreaking. When Babylonian engineers needed to ensure a ziggurat's terraces maintained uniform angles, they could consult these precalculated ratios to determine ramp slopes and step heights. Irrigation channels requiring specific gradients to maintain water flow. The tablet provided instant reference for elevation changes over distance. Even more impressively, the value's precision suggests the Babylonians understood something modern architects grapple with, that tiny variations in angle ratios dramatically affect structural integrity. One triangle on the tablet with sides 119, 120, and 169 forms an angle of 44.76 degrees, a near-perfect match for the ideal slope preventing mudbrick erosion in Mesopotamia's seasonal rains. What truly astonishes is how these ancient mathematicians derived their results. Analysis shows they likely used reciprocal pairs numbers that multiply to 1 in their base 60 system to generate Pythagorean triples through algebraic manipulation. Essentially, they'd select 2 numbers where 1 was a reciprocal, like 2 and 0.5, then applied geometric formulas to produce whole number triangle sides. This method, rediscovered by Greek mathematicians over a millennium later, proves Babylonian mathematics wasn't just arithmetic, it was abstract reasoning of the highest order. The tablet even contains subtle corrections where scribes adjusted values for greater accuracy, showing an iterative approach to mathematical refinement we associate with modern scientific method. Perhaps most remarkably, Plimpton 322's geometry extended beyond practical construction. Some scholars believe its trigonometric sequences help track celestial movements, with the decreasing ratios mirroring how planetary positions change angular velocity in elliptical orbits. When moonlight struck a ziggurat's precisely angled staircases during certain festivals, it wasn't just beautiful, it was geometry speaking the language of the gods. This humble clay fragment didn't just measure triangles, it encoded an entire worldview where mathematics bridged earth and heaven, one perfect right angle at a time. High in the Andes, the Incas' earthquake-proof walls stand as silent guardians of ancient geometric wisdom where massive, irregular stones interlock so precisely, not even a blade of grass can slip between them. This isn't just impressive craftsmanship, it's a masterclass in applied polygonal mathematics. Unlike the straight lines of European masonry, Inca builders employed a dynamic geometry of convex and concave polygons that transformed walls into three-dimensional jigsaw puzzles. Each stone's edges were calculated to distribute seismic energy along multiple vectors when an earthquake strikes. These walls don't just resist collapse, they dance, with stones momentarily shifting before settling back into perfect alignment. The secret lies in the angles. While most cultures used 90-degree corners, Inca masons cut stones with 12 or 14 unique angles per block, creating interlocking teeth that resist shearing forces. Modern engineers have discovered something astonishing. These angles often fall within 5 to 10 degrees of each other, forming subtle geometric patterns that repeat across entire walls like fractal waves. The famed 12-angle stone in Cusco's Hatanrumiok Street demonstrates this perfectly. Its 12 carefully beveled edges don't just fit neighboring stones, they create a distributed load system where any impact gets dispersed through 12 different contact points simultaneously. Laser scans reveal even more brilliance in the mortarless joints. The contact surfaces between stones aren't flat but slightly convex, allowing micro-movements during tremors while maintaining structural integrity. This convexity follows precise curvature ratios, typically matching the natural arch formed when a chain hangs between 2 points, a catenary curve. The same geometry Gaudí used centuries later in his earthquake-resistant Barcelona arches. Some temple walls incorporate graduated stone sizes, with larger blocks at the base forming a logarithmic spiral that channels vibrations upward and outward like a geometric shock absorber. Perhaps most remarkably, the Incas encoded this seismic wisdom in their architecture's proportions. At Machu Picchu, retaining walls tilt inward at angles matching the surrounding mountain slopes, typically 6 to 8 degrees, creating a unified geometric resistance against landslides. The trapezoidal doorways found in sacred sites aren't just stylistic. Their angled sides approximate 58 degrees, the optimal incline for withstanding both lateral shaking and vertical compression forces during quakes. Even the famous, battered walls thicker at the base follow mathematical sequences where each course of stone steps inward by precisely 1/20th of its height, distributing weight along calculated vectors. The real revelation comes when you witness these principles in action. During the 2007 Pisco earthquake, modern concrete structures crumbled while 600-year-old Inca walls in the Sacsayhuaman fortress barely trembled. Those jagged zigzag patterns along its battlements, they're not decorative. Each zig forms a 60-degree energy-dissipating joint that breaks destructive wave patterns. This living geometry proves the Incas didn't just build walls, they engineered stone symphonies where every angle sings in harmony with the earth's vibrations. Buried in the hymns of the ancient Vedas lies a geometric puzzle that would baffle modern mathematicians: the precise construction of the Agni, the sacred fire altar. These weren't just piles of bricks for rituals, they were three-dimensional textbooks of Indian mathematics, where every layer and angle encoded cosmic truths. The most complex altars, like the falcon-shaped Siena Chiti, required stacking over 1,000 bricks in 7 precise layers, each following geometric rules that would make Euclid pause. But here's what's astonishing. The altar's proportions often converged on the value of pi and the square root of 2 with accuracy that shouldn't exist in 1500 BC. The Shatapatha Brahmana text reveals the geometric wizardry behind these constructions. To build the basic circular altar, priests would begin with a square divided into 7 equal parts, a feat requiring advanced fractional understanding. They'd then inscribe a circle within this square whose circumference matched the square's perimeter when converted through precise ratios. This forced the circle's diameter to approximate pi's value as 22 divided by 7, a fractional estimate accurate to 2 decimal places. Even more impressive were the elongated altars designed to amplify ritual power, their lengths precisely 1 1/3 times their widths, a ratio generating a diagonal matching the square root of 2 to within 0.016%. Archaeologists have discovered these mathematical constants echoed in the altar's physical remains. At the site of Kalibangan, fire altars show bricks arranged in fractal-like patterns, smaller squares within larger ones, all maintaining consistent proportional relationships. Some elongated altars display brick courses that decrease in number as they rise, following sequences that mirror what we now call harmonic progressions. The most sophisticated designs, like the tortoise-shaped Kerma Chiti, used 5 layers of bricks arranged in concentric squares and circles, with the area ratio between layers encoding the approximate value of phi, the golden ratio. The altar's geometry wasn't just mathematical exhibitionism, it served profound cosmological purposes. Vedic texts explicitly connect altar dimensions to time itself. One altar's area equals the number of syllables in a sacred chant, which in turn matches the days in a 5-year lunar cycle. The positioning of breath bricks along cardinal axes created invisible geometric channels believed to conduct spiritual energy. When priests rebuilt altars after each ritual, a requirement that demanded perfect recreation, they weren't just performing rote actions but reinforcing the Hindu concept that the universe itself constantly recreates through geometric laws. Perhaps most remarkably, these designs bridged abstract math and practical astronomy. Certain fire altars in the Ganges Valley align so the rising sun on summer solstice strikes a designated eye brick at a specific angle, while the altar's shadow at winter solstice traces a perfect isosceles triangle on ritual grounds. Modern scholars have found that some altar dimensions correspond to the angular size of the sun's disk at certain latitudes, proof that these weren't just ritual objects but functioning astronomical instruments. When you examine the precise corners of a 3,000-year-old Agni replica today, you're not looking at primitive religion but at the birthplace of Indian trigonometry. Those carefully angled bricks whisper a revolutionary truth, that spirituality and science once spoke the same language, written in the flawless grammar of sacred geometry. The Pantheon's dome isn't just an architectural marvel, it's a frozen moment of geometric perfection, where every curve whispers a mathematical secret. That iconic hemispherical dome, still the world's largest unreinforced concrete vault after 2,000 years, follows a ratio so precise it feels divine. Its height from the floor to the oculus matches exactly its interior diameter, 43.3 meters. This creates a perfect sphere that could fit snugly inside the rotunda, touching the floor and the dome's crown simultaneously. But the real magic lies in the oculus, that 9-meter-wide opening at the apex acting as both structural masterstroke and celestial calculator. Its diameter isn't arbitrary, it's precisely 1/5 of the dome's height, a proportion that distributes weight along the dome's meridians like the spokes of a cosmic wheel. Roman engineers didn't achieve this harmony by accident. The dome's thickness graduates with geometric ingenuity, thick at the base where stress concentrates, tapering to a feather-light 1.4 meters near the oculus. This thinning follows a logarithmic curve mirroring the natural distribution of forces in a hemispherical shell. Even the coffers, those recessed square panels adorning the ceiling, aren't merely decorative. Their 5 concentric rows decrease in size as they ascend, mathematically compensating for the dome's curvature to maintain visual harmony from below. Modern laser scans reveal their dimensions follow the Fibonacci sequence, reducing by approximately 0.618 the golden ratio with each tier. The oculus itself is a geometric paradox, an open circle that somehow strengthens the dome rather than weakens it. By removing weight at the critical stress point, it transforms what would be compressive forces into tensile ones, allowing the dome to breathe and flex under thermal expansion. Sunlight streaming through this opening traces a path that doubles as an astronomical instrument. At midday on the spring equinox, the light beam strikes a grill above the doorway, a precision alignment proving the pantheon's geometry synchronizes with celestial movements. During rain, water falling through the oculus drains through 22 nearly invisible holes in the sloped marble floor, their placement forming a dodecagon 12-sided polygon that echoes the dome's hidden structural ribs. What few notice is how the dome's geometry manipulates perception. The floor's subtle convex rise just 12 centimeters over 40 meters counters the dome's optical illusion of sagging. Columns along the rotunda lean inward by 6 centimeters. If extended upward, they'd meet 3 kilometers high, creating an invisible pyramid that stabilizes the composition. Even the materials follow geometric logic. Heavier basalt aggregate near the base gradually shifts to lightweight pumice at the summit, a calculated density gradient that anticipates modern engineering principles by millennia. Stand beneath that oculus today, and you're not just seeing sunlight, you're witnessing the moment Roman concrete met celestial mathematics. Every measurement, every proportion whispers of an empire that didn't just build domes, but sculpted space itself with the compass of the gods. The Eye of Horus wasn't just a mystical symbol, it was ancient Egypt's most ingenious mathematical toolkit, disguised as a divine emblem. This sacred icon, depicting the falcon god's segmented eye, contains one of history's earliest geometric series hidden in plain sight. Each part of the eye corresponds to a unit fraction, a fraction with 1 as its numerator, creating a perfect visual representation of powers of 1/2. The right side of the eye equals 1/2, the pupil 1/4, the eyebrow 1/8, and so on down to 1/64. Together, these fractions don't just adorn amulets, they form a 6-term geometric progression summing to 63/64, astonishingly close to the whole. The brilliance of this system emerges in practical applications. Egyptian architects used these fractions as modular measurements when constructing temples, dividing cubit rods into precise portions mirrored by the eye's segments. A surviving wooden tablet from the Middle Kingdom shows how builders would mark columns using these fractions, the 1/2 segment for major divisions, the 1/64 for fine adjustments no wider than a grain of barley. What seems like religious imagery actually functioned as an architectural protractor, with the curved lower eyelid serving as a template for carving perfect column drums. But the geometric genius goes deeper. The missing 1/64 that prevents the series from totaling 1 wasn't an error. It reflected Egyptian understanding of infinite series convergence. Myth explained it as the magic thought used to restore Horus's eye, but mathematically it represents how infinite having approaches but never reaches 0. Scribes exploited this property in division problems, using the eye's fractions as reference points. The Rind mathematical papyrus shows how they'd multiply by adding eye segments. To divide 3 by 4, they'd take the 1/2 and 1/4 portions together. The fractions even encoded celestial knowledge. Certain temple ceilings depict the eye aligned with constellations, where each fraction represents fixed angular distances, the 1/8 segment matching the width of Orion's belt when observed from Thebes. Modern recreations prove that by holding a marked eye of Horus at arm's length during specific lunar phases, priests could estimate the moon's apparent diameter to within 5% accuracy. This wasn't mysticism, it was portable spherical geometry, where mythology and mathematics fused into a single sacred instrument. Perhaps most remarkably, the eye's proportions mirror those of actual human vision. The 1/2 segment approximates the monocular field of view, while the 1/64th matches the minimum angle of resolution for distinguishing stars. When an Egyptian artisan carved this symbol into a tomb wall or measured medicine with its fractions, they weren't just following tradition. They were wielding a 3,000-year-old geometric compass, one that measured everything from temple walls to the heavens themselves with the precision of a divine blueprint. Plato saw geometry as the language of creation itself, and nowhere is this more evident than in the 5 perfect forms that bear his name, the Platonic solids. These shapes, with their identical faces, equal angles, and symmetrical perfection, weren't just mathematical curiosities to the ancient Greeks. They were the building blocks of reality, each assigned to a fundamental element of nature. The tetrahedron, with its sharp edges and 4 triangular faces, embodied fire's piercing energy. Earth took the form of the stable cube, its 6 square faces symbolizing solidity. The octahedron's 8 triangles mirrored air's lightness, while the 20-faced icosahedron with its fluid contours represented water's adaptability. The dodecahedron, with 12 pentagonal faces, was reserved for the heavens, a shape so divine Plato wrote that the god used it for arranging the constellations on the whole heaven. Nature seems to whisper the truth of Plato's vision. Crystals of pyrite naturally form perfect cubes, while the tetrahedral structure of methane molecules reveals fire's geometry at the atomic level. Viruses like the adenovirus adopt icosahedral shells, their 20 faces providing optimal strength for microscopic survival. Even the cosmos obeys these ancient rules. Recent observations suggest the large-scale structure of the universe may approximate a dodecahedral pattern, echoing Plato's celestial assignment. Architects across millennia have harnessed this sacred geometry. The tetrahedron reappears in the sloping roofs of Gothic cathedrals, channeling spiritual aspiration skyward. Cubes anchor Islamic architecture's tilework, their repeating squares symbolizing earthly order. Buckminster Fuller's geodesic domes translate the icosahedron into sprawling structures, proving that 2,000 years after Plato, these shapes still hold structural wisdom. Modern chemistry confirms their enduring power, carbon atoms arranging themselves into tetrahedral bonds to form diamonds, while water molecules cluster in transient icosahedral patterns during freezing. What makes these forms truly timeless is their mathematical inevitability. They're the only possible convex shapes with identical regular polygons for faces and equal angles at every corner, a fact proven by Euclid and celebrated in Kepler's planetary models. When a Roman craftsman carved a dodecahedron in stone or a medieval alchemist drew tetrahedral symbols, they weren't just following tradition. They were touching the same geometric truth that governs everything from salt crystals to spiral galaxies, a reminder that perfection hides in plain sight, waiting to be measured. Inside the palaces of ancient China, bronze dragons stood guard not just as symbols of power, but as sophisticated earthquake detectors, ingenious devices that used pendulum geometry to sense tremors across vast distances. These ornate vessels, often shaped like mythical beasts with articulated jaws, contained a hidden masterpiece of mechanical precision. At their core swung delicately balanced bronze balls, each suspended by thin rods at calculated angles corresponding to different seismic wave thresholds. The slightest ground motion would trigger a chain reaction of geometric cores and affect pendulums swinging in precise arcs until their weight struck resonant bronze plates, announcing danger with thunderous clarity. The system's brilliance lay in its graduated sensitivity. 8 dragons typically surrounded a central toed figure, each pendulum tuned to respond to distinct vibrational frequencies. Dragons facing cardinal directions had suspension rods angled at 55 degrees to detect primary waves, the fast-moving compression waves that arrive first during quakes. Their closely spaced jaws held balls ready to drop at the slightest longitudinal vibration. Secondary dragons, positioned at intercardinal points, used 45-degree suspensions to catch slower secondary waves that ripple side to side. This geometric arrangement allowed officials to pinpoint an earthquake's direction by noting which dragon discharged its ball first, while the sequence of subsequent drops revealed the epicenter's approximate distance. Modern engineers have recreated these devices with startling results. When subjected to seismic tests, replicas responded to quakes as weak as magnitude 4 from over 200 kilometers away, comparable to early 20th century seismographs. The key was the pendulum's elliptical swing paths, geometrically constrained by curved tracks that amplified subtle motions. As primary waves compressed the ground vertically, the angled rods transformed this motion into exaggerated horizontal swings through trigonometric transfer. A 2-centimeter vertical displacement could become a 15-centimeter pendulum swing, enough to trip the release mechanism. The detector's precision went beyond simple mechanics. Some vessels incorporated tuned resonators bronze chambers filled with water to specific levels that would slosh at frequencies matching regional earthquake profiles. At the ancient capital of Loyang, archaeologists uncovered a detector array where directional dragons stood on stone platforms carved with spiral grooves. These grooves acted as waveguides, channeling surface waves toward particular pendulum systems while dampening false signals from nearby traffic. The entire assembly formed a seismic antenna, its geometry refined through centuries of observation. Perhaps most remarkably, these bronze sentinels anticipated modern network seismology. Han Dynasty records describe linking detectors across multiple cities. When one sounded, messengers would note the time and dispatch riders to compare notes. By calculating differences in arrival times between stations, officials could triangulate quake locations with surprising accuracy. The dragons didn't just sense earthquakes, they revealed China's landscape as an interconnected geometric web, where bronze and mathematics transformed imperial palaces into the world's first seismic observatories. Climbing the ancient steps of El Castillo, the great Mayan pyramid at Chichen Itza, visitors discover an eerie acoustic phenomenon. A sharp, metallic chirp echoes back with each footfall, as if the stones themselves are singing. This isn't accidental architecture, it's sonic geometry meticulously engineered into the pyramid's very bones. The secret lies in the staircase's exacting proportions. Each of the 91 steps, totaling 365 when including the temple platform, acts as a sound diffuser, with treads and risers cut at angles that transform human footsteps into high-frequency chirps. When a hand clap or shout strikes these precisely aligned surfaces, sound waves reflect off the step terraces in phased sequences, creating interference patterns that amplify certain frequencies while canceling others. The result, a series of rapid, bird-like pulses that seem to dance across the plaza. An auditory illusion so precise, researchers initially mistook it for hidden sound devices. But the true genius emerges during rituals. During equinoxes, when the setting sun casts serpent-shaped shadows down the pyramid's northern staircase, the acoustic effects reach their peak. The pyramid's 4 staircases form a giant quadrilateral loudspeaker of sorts. Sound waves traveling up one side reflect off the temple platform and cascade down the opposite stairs in cascading echoes. Calculations show the intervals between these reflections match the natural reverberation time of the human voice at this frequency range, meaning a priest chanting from the summit would hear their own voice returning in rhythmic waves, perfectly synchronized with the shadow play below. It's no coincidence the Maya revered the Quetzal bird, whose cry mirrors these synthetic chirps. Architecture and nature harmonized through geometry. Laser scans reveal even deeper intentionality. The staircase's average 25-degree slope isn't arbitrary. It's the ideal angle to reflect sound at frequencies between 2,000 and 3,000 Hz, the range where human ears are most sensitive. Each step's nose projects slightly beyond the one below, creating a series of miniature diffraction edges that scatter sound in controlled patterns. When archaeologists recreated the stairs with a mere 5 mm deviation in these overhangs, the chirp effect disappeared entirely. This precision suggests the Maya didn't just stumble upon these acoustics, they calibrated them, likely using water-filled resonance chambers found beneath nearby structures to test sound propagation during construction. The pyramid's sonic geometry extends beyond stairs. The temple atop El Castillo features narrow, corbelled doorways that function as acoustic filters, their trapezoidal shape attenuating low frequencies while allowing high-pitched chirps to pass unobstructed. Courtyard walls angle inward to create a whispering gallery effect, where spoken prayers could travel hundreds of feet with unnatural clarity. Even the plaza's paved surface plays its part. The limestone slab's porosity was carefully graded, with denser stones near the pyramid creating reflective zones and more absorbent ones further out to prevent echo clutter. What seems like supernatural audio engineering served profound spiritual purposes. The chirping echoes may have represented the voices of ancestors or deities, with the pyramid acting as a giant spiritual radio receiver. During ceremonies, priests could have used the acoustics to create the illusion of invisible beings responding to human invocations, a theatrical trick powered by pure geometry. When the evening breeze sweeps across those weathered steps today, it doesn't just carry sounds, it carries the ghostly imprint of a civilization that turned stone into song and mathematics into magic. Buried in the sun-baked soil of ancient Mesopotamia, boundary stones known as kuduras stood as legal guardians of farmland, but these weren't simple property markers. Each carved stone was a geometric cipher, encoding land measurements through a brilliant system of similar triangles that allowed even illiterate farmers to verify their field's dimensions. The key lay in their trapezoidal bases, carefully shaped blocks with two parallel sides cut at consistent angles. When placed along a field's perimeter, these stones created a network of reference points that surveyors could use to reconstruct boundaries with mathematical certainty. The system worked through projective geometry centuries before it was formally defined. Surveyors would plant stones at each corner of a triangular plot, ensuring their angled sides pointed toward central reference monuments. If a dispute arose, officials could stretch ropes between the stones, creating intersecting lines that formed similar triangles to the original survey. By measuring just one side and its corresponding angles, a technique called triangulation, they could calculate the entire plot's area without walking its perimeter. Some kuduras even featured drilled holes at specific heights, allowing sunlight to pass through at certain times of day and cast verifying shadows across measurement lines. What made this system revolutionary was its error-proof design. The stone's standardized angles, typically 45 or 60 degrees, ensured that any disturbed marker would visibly disrupt the geometric harmony when ropes were stretched. Farmers could spot tampering instantly if the ropes no longer aligned with carved grooves on adjacent stones. The Code of Hammurabi prescribed harsh penalties for moving these markers precisely because their mathematical relationships made theft undeniable. Modern excavations reveal astonishing precision in these ancient surveys. At Nippur, archaeologists found a field divided by stones spaced exactly 72 cubits apart, a distance that formed perfect equilateral triangles with nearby canal markers. Cuneiform tablets describe how surveyors used bronze angle rods to verify stone alignments, achieving accuracy within half a degree. Some boundary stones even incorporated scale diagrams of the fields they demarcated, with proportions maintained so precisely that modern cartographers can overlay them onto satellite images with minimal distortion. The true brilliance emerges in how these stones encoded three-dimensional data. Curved notches along their edges represented elevation changes, allowing reconstruction of terraced fields' contours. A series of stones near show graduated symbols, each additional wedge indicating a 1-cubit rise in elevation across the plot. This meant a farmer could calculate irrigation requirements simply by counting symbols between boundary markers, transforming stone geometry into an ancient spreadsheet of land productivity. These silent sentinels did more than mark territory. They turned the Mesopotamian landscape into a living graph paper where every furrow and canal existed in precise geometric relationship. When sunlight strikes one of these weathered stones today, it illuminates not just cuneiform inscriptions, but humanity's first steps toward the geometric cadastral systems that still define property boundaries worldwide. Imagine standing in the scorching Egyptian noon, where the shadow of an obelisk shrinks to a dark pool at its base. This was humanity's first encounter with solar geometry transformed into a clock. The Egyptians didn't just track time, they choreographed it with shadows, using sundials whose designs evolved into stunning complexity across civilizations. Their earliest models, simple horizontal plates with raised gnomons, worked perfectly near the Nile's latitude, but as sundial technology traveled to Greece and Rome, artisans faced a geometric puzzle: how to adapt these timekeepers for lands where the sun traced different arcs across the sky. The Egyptians' flat sundials thrived at lower latitudes because the sun's path there is nearly vertical. A basic design, a T-shaped bar casting shadows onto marked limestone, sufficed for dividing daylight into 12 equal hours. But travel north to Athens, and the sun's lower angle rendered Egyptian dials inaccurate by midday. Greek mathematicians responded with hemispherical dials, carving bowl-shaped depressions into marble where a central gnomon's shadow would curve along hour lines calculated for their latitude. These scaff dials didn't just tell time, they modeled the celestial sphere itself, their concave surfaces mirroring the dome of the sky. The hour lines, radiating from the gnomon's base like spokes, followed precise angles derived from the sun's maximum altitude at summer solstice, a calculation requiring understanding of spherical geometry that wouldn't be formalized for centuries. Rome's empire building necessitated even more sophisticated adaptations. Portable sundials became essential for officials traveling from Britain to Egypt, leading to the invention of the hemicyclium, a folding bronze dial with adjustable gnomon angles. A legionnaire in Britannia would tilt the gnomon to match local latitude about 51 degrees, creating hour lines spaced wider than those used in Mediterranean models. The Romans' genius lay in standardizing these designs. Archaeological finds revealed dials with interchangeable plates for different latitudes, their engraved curves following precalculated solar trajectories. One remarkable example from Pompeii features 7 adjustable gnomons, each calibrated for major imperial cities, a geopolitical clock where geometry served as the empire's temporal glue. What unified these designs was their reliance on the gnomon's angle, always set parallel to Earth's axis. Egyptian obelisks and Greek needle gnomon sundials all pointed toward celestial north, their shadows rotating at 15 degrees per hour, Earth rotation rate divided by 24 hours. But Roman engineers took this further, inventing the analmatic sundial, a horizontal plate where the user themselves became the moving gnomon. Standing on a date-marked stone, their shadow would fall onto hour lines calculated through stereographic projection, a geometric technique later used in Renaissance mapmaking. The true test of these systems came at extreme latitudes. In northern Roman outposts like Hadrian's Wall, traditional sundials failed during summers near perpetual daylight. Local artisans responded with conical dials whose spiraling hour lines accounted for the sun's shallow diurnal circles, a solution rediscovered during the Arctic expeditions of the 19th century. Meanwhile, Egyptian water clocks often supplemented sundials at night, their flow rates adjusted seasonally using solar geometry tables, proving ancient timekeeping wasn't merely mechanical, but a continuous dialogue between shadow, angle, and flow. When you compare a vertical Roman sundial still standing in the Forum to the fragment of a Greek hemicycle in the Athens Agora, you're not just seeing different cultures' approaches to time. You're witnessing the birth of globalized science where geometry became the universal language bridging deserts, mountains, and seas, one precisely angled shadow at a time. Lay your palm against the cool metal surface of a Sri Yantra, and you're not just touching a piece of sacred art, you're connecting with a 2,000-year-old geometric meditation machine. These intricate diagrams, etched onto copper plates or drawn with ritual precision, represent the pinnacle of Hindu sacred geometry, where mathematics and spirituality merge into a single transformative experience. At first glance, the Sri Yantra appears as an elegant nest of interlocking triangles, but hidden within its symmetrical beauty lies a complex architectural blueprint for cosmic energy. The foundational geometry reveals itself in layers: 9 triangles, 4 pointing upward to represent masculine divine energy, 5 descending for feminine power, intersect to form 43 smaller triangles through precise angular relationships. Each intersection occurs at exactly 51.8 degrees, the golden angle found throughout nature from sunflower seed spirals to galaxy arms. The outer square frame, representing earthly existence, holds 2 concentric circles symbolizing the transition between material and spiritual realms, all proportions carefully calculated so the entire diagram can be constructed using only a straight edge and compass, yet containing mathematical relationships that would take modern algebra to fully decipher. What makes these yantras truly extraordinary is how they guide the meditator's mind. The central point, or bindu, serves as both geometric origin and spiritual focus, a singularity where all lines converge. Radiating outward, the intersecting triangles create optical vibrations that naturally draw the eye inward through a process called active stillness. Neuroscientists studying meditation have discovered something remarkable. Focusing on the Sri Yantra's patterns produces brainwave synchronization between the occipital lobe visual processing and parietal lobe spatial awareness, creating the ideal neural state for deep contemplation. The mathematics governing these diagrams goes far beyond simple symmetry. Certain yantras encode the Fibonacci sequence in their concentric square layers, while others feature lotus petals arranged in prime numbers 11, 13, 17, believed to resonate with specific cosmic frequencies. The Sri Yantra's proportions perfectly balance the circle's circumference to its enclosing square's perimeter in a ratio matching the Earth's axial tilt, 23.5 degrees. When priests chant mantras while meditating on these designs, the sound vibrations interact with the geometric patterns in ways modern cymatics research is only beginning to understand, visible ripples forming harmonic shapes that mirror the yantra's angles. Archaeologists have uncovered yantra-engraved stones at ancient Indian university sites like Nalanda, where scholars used them as teaching tools for advanced geometry. The surviving palm leaf manuscripts reveal construction methods requiring 24 precise steps, from establishing the cardinal axes to plotting the recursive triangles, a process taking trained artists weeks to complete. Some temple yantras, like those at Khajuraho, incorporate 3-dimensional versions where carved stone channels direct water to flow along sacred geometric paths during rituals, turning fluid dynamics into a meditation on impermanence. The true power of these meditation diagrams emerges in their practical application. Contemporary mathematicians have analyzed the Sri Yantra's proportions using vector geometry, discovering that its line intersections create perfect logarithmic spirals, the same growth pattern found in hurricanes and spiral galaxies. When Buddhist monks create sand mandalas, the yantra's Tibetan cousins, they're not just making art but physically manifesting these universal geometric principles only to dissolve them, teaching detachment through mathematics. The next time your eyes trace the labyrinthine paths of a yantra's design, remember, you're not just looking at shapes but participating in an ancient experiment where human consciousness meets the fundamental geometry of existence itself. The Roman legion didn't just march into battle, they transformed into living geometry, their formations calculated with the precision of a master architect's blueprint. Among their most formidable creations stood the testudo, or tortoise, a defensive masterpiece where overlapping shields formed an impenetrable polyhedral shell. This wasn't just brute strength, it was applied mathematics in motion. Picture this: 60 men moving as one, their rectangular scutum shields angled at exactly 22 degrees to create interlocking coverage. The front rank held shields vertically, forming a flat plane resistant to frontal assault, while subsequent ranks raised theirs overhead in a convex curve, their edges overlapping like scales to deflect arrows and stones. The geometric genius: each shield's curvature and weight distribution allowed it to bear the load of those above while maintaining mobility, a feat requiring precise calculations of angle, friction, and collective balance. But the testudo's power went beyond static defense. When advancing toward enemy walls, the formation morphed into a dynamic ramp, its rear ranks gradually elevating their shields to form an inclined plane matching the siege ladder's optimal 35-degree angle. Engineers had determined this slope through trial and error, recognizing it as the geometric sweet spot between stability and accessibility. Even the soldiers' spacing followed mathematical rules. Each man occupied a square of precisely 3 Roman feet per side, ensuring enough room to maneuver while maintaining shield cohesion. Modern reconstructions show this spacing created a honeycomb-like structure where stress distributed evenly across the formation. When one shield took an impact, the force diffused through 6 adjacent contact points. The Romans didn't stop at defensive geometry. Their offensive triangular wedge, the cunius, turned human bodies into a living battering ram. Soldiers arrayed themselves in successive rows of increasing numbers, 4 men in the front, 7 behind them, then 10, forming an isosceles triangle that concentrated force toward its apex. The formation's 45-degree flank angles allowed it to penetrate enemy lines like a geometric laser, splitting opposing forces while minimizing exposure. Legionnaires trained to maintain exact spacing, their gladius thrusts synchronized to exploit gaps created by the wedge's angular momentum. Perhaps most strategically brilliant was the checkerboard manipular formation, where units deployed in quincunx patterns like dots on a 5-faced die. This alternating grid created kill zones where enemy charges would funnel into pre-calculated traps, while allowing Roman reserves to pivot along diagonal lines of reinforcement. The spacing between maniples followed the golden ratio, close enough for mutual support, but distant enough to prevent encircling, a balance Vegetius described as geometry in service of blood. When Hannibal's cavalry outflanked them at Cannae, the Romans adapted by inventing the orbis, a perfect defensive circle with radially aligned shields and spears projecting at 70-degree intervals to maximize coverage, a formation so geometrically sound it inspired medieval infantry tactics 1,000 years later. These weren't just fighting techniques, they were equations made flesh, where every angle and interval had been refined through generations of campaign mathematics. The testudo's curvature matched the parabolic trajectory of Persian arrows. The cunius's apex angle corresponded to the human field of vision's focal point. Even the legion's iconic marching columns moved at a pace calibrated by geometric progression. Each soldier's stride length multiplied by unit depth to ensure arrival at battlefields with energy reserves optimally preserved. When sunlight flashed off those ordered ranks of shields and spears, it didn't just dazzle enemies, it illuminated history's first fully mathematicized army, turning warfare into a grim but glorious exercise in applied Euclidean logic. High above the sarcophagi of Egyptian pharaohs, the ceilings of tombs and temples reveal a celestial secret, a sophisticated star clock system that turned the night sky into a geometric timekeeper. These intricate diagonal star tables, painted in precise grids across chamber ceilings, weren't mere decorative astrology. They functioned as the ancient world's most elegant celestial clocks, tracking hours through the measured movement of constellations. Each tableau divides the night into 12 equal segments, with diagonal lines connecting Deccan stars' specific constellations that rose consecutively on the horizon throughout the year. A priest or astronomer would lie beneath this painted cosmos, comparing the real night sky outside to the fixed positions above. reading time as clearly as we might glance at a wristwatch. The genius lies in the table's geometric adaptation. Unlike modern clocks with uniform hours, Egyptian star clocks accounted for the night's changing duration across seasons. During summer's short nights, the decans appeared to move faster across the sky, while winter's long nights stretched their progression. The diagonal lines on these charts cleverly compensated for this variance: steeper angles for summer months when stars raced across the sky, shallower slopes for winter's languid pace. This created a self-adjusting system where each diagonal row represented a 10-day period, with star positions shifting incrementally to stay synchronized with Earth's rotation. Take the ceiling of Senenmut's tomb, where the goddess Nut arches across a meticulously plotted grid. 36 decans groups of stars that rose just before dawn at 10-day intervals are arranged in 2 parallel diagonal bands. The upper band tracks the 12 hours of night, while the lower band correlates these to the annual civil calendar. By observing which decan aligned with the meridian, an imaginary north-south line, Egyptians could determine the hour with astonishing accuracy. Modern simulations show these tables were accurate to within 15 minutes, a precision achieved through generations of observational refinement. But the true geometric mastery emerges in the table's 3-dimensional thinking. Some temple ceilings, like those at Dendera, feature dual star clocks on different planes, one for the observed sky, another inverted to represent the underworld's mirrored realm. The diagonal grids intersect at specific angles corresponding to the Nile's flooding season, suggesting the clocks also served as agricultural calendars. Certain stars, like Sirius, received special marking. Their first annual appearance, heliacal rising, signaled the flood's arrival, an event so critical it reset their lunar calendar. The table's diagonal lines often converge toward depictions of the bull's foreleg, the Big Dipper, which Egyptians believed anchored the northern sky like a cosmic pivot. What seems like abstract artistry reveals rigorous mathematical planning. Analysis of the Ramesseum star ceiling shows the diagonal lines follow a consistent trigonometric relationship. The angle between consecutive decan lines matches the average daily displacement of stars at Thebes' latitude. Some tables even incorporate corrections for precession, the gradual shift in stellar positions over centuries, proving these weren't static diagrams but evolving scientific documents. When sunlight penetrates tomb shafts to illuminate specific decans on solstice mornings, it's not just light touching paint. It's the meeting point of celestial mechanics and human ingenuity, where geometry bridged the fleeting present and the eternal heavens. Pythagoras didn't just discover mathematical theorems, he heard geometry sing. Walking past a blacksmith shop one day, the ancient Greek philosopher noticed something extraordinary. The hammers striking different-sized anvils produced musical intervals that corresponded to simple whole number ratios. The heaviest hammer, weighing exactly twice as much as another, sounded a pitch 1 octave higher, a ratio of 2 to 1. Other hammers produced perfect fourths and fifths at ratios of 4 to 3 and 3 to 2. This revelation sparked an entire philosophy where music and mathematics intertwined, revealing that harmony wasn't just an art, it was geometry made audible. At the heart of this discovery lay the monochord, a single-stringed instrument that became Pythagoras' laboratory for unlocking the universe's sonic code. By dividing the string at precise fractions, he demonstrated that consonant intervals emerged from clean geometric divisions. Plucking a string divided in half produced that octave, while a 2/3 division created a fifth and 3/4 a fourth. What seemed like aesthetic preference turned out to be irreducible mathematical truth. The simpler the ratio between string lengths, the more harmonious the sound. These ratios didn't just define scales, they structured reality itself, appearing in planetary orbits, architectural proportions, and even the spiral of nautilus shells. The Greeks took this further with their system of tetrachords, 4-note scales spanning a perfect fourth, stacked to build modes like Dorian and Phrygian. Each mode had its own geometric fingerprint. The Dorian's intervals followed a ratio sequence of 9 to 8 whole tone and 256 to 243, a tiny semitone called the limma, creating a distinct emotional character. Architects soon adapted these ratios, designing temples where column spacing mirrored musical intervals, a practice seen in the Parthenon's facade, where the distance between columns matches the ratio of a perfect fourth, making the structure visually harmonious to passers-by. Modern physics confirms the Greeks' intuition. When two notes sound consonant, their sound waves intersect at regular intervals dictated by these same ratios, creating stable interference patterns. Dissonant intervals produce chaotic clashes, a phenomenon visible in cymatics experiments where sand particles on vibrating plates form intricate geometric shapes for consonant frequencies but disordered blobs for dissonant ones. The Greeks may not have known about sound waves, but their geometric approach to harmony anticipated Fourier analysis by millennia. Perhaps most astonishing is how these ratios transcend culture. A Chinese gyukan zither's harmonic nodes, an Indian sitar's frets, and a West African balafon's bars all align with Pythagorean proportions, proving that this geometric language of music is universal. When you hear a guitar's perfect fifth today, you're not just enjoying a musical interval, you're hearing the echo of a 2,000-year-old mathematical truth, one that still resonates at the intersection of art and science. The earliest Chinese compasses weren't just tools for navigation, they were intricate geometric calculators, encoding the cosmos into a bronze disc no larger than a human palm. These ancient devices, known as Sinan or south-pointing compasses during the Han Dynasty, didn't merely indicate direction. They divided the horizon into a precise 24-part grid, each segment a calculated window into celestial harmony. At the heart of this system lay the earthly branches and heavenly stems, a fusion of astronomy and mathematics that transformed a simple magnetic needle into a multidimensional coordinate system. The compass's circular plate mirrored the heavens, with the 24 directions arranged like spokes on a cosmic wheel. Each segment represented 15 degrees of the full 360-degree circle, but these weren't arbitrary divisions. They correlated with the solar year, 24 fortnightly periods known as Jiki, marking seasonal transitions from spring begins to great cold. The directions also aligned with the 24-hour day, creating a time-space continuum where rotating the compass became an act of synchronizing human activity with celestial rhythms. What made this system geometrically brilliant was its nested symmetry. The primary 8 directions, north, northeast, east, etc., formed an octagon, with each further divided into 3 not equal parts, but proportions reflecting traditional Chinese fractional mathematics. Northeast, for instance, split into northeast by north, true northeast, and northeast by east, with angular offsets of 3 3/4 degrees between submarkings. These precise subdivisions allowed navigators to correct for magnetic declination centuries before Europeans recognized the phenomenon. The markings weren't static either. Advanced compasses featured rotating inner rings with eclipse prediction scales, their gear teeth matching the angular increments of lunar nodes. The compass's geometric logic extended beyond the physical. Its directions corresponded to the 24 pentatonic modes in ancient Chinese music theory, each orientation believed to resonate with specific cosmic frequencies. Architects used these same divisions to align buildings. The Forbidden City's layout precisely follows compass-derived angles, with major gates offset exactly 7.5 degrees from cardinal points to harmonize with Feng Shui calculations. Even the needle's pivot point held geometric significance, positioned not at the disk's center but slightly offset to account for the magnetic pole's annual drift, a correction that required solving spherical trigonometry problems without modern notation. Surviving Ming Dynasty compasses reveal astonishing precision. One specimen in the Shanghai Museum features a directional grid etched using a compass and straightedge technique that divides the circle into 24 parts with an error margin of less than half a degree. The outer ring displays 365 1/4 notches, an explicit nod to the solar year's duration, while the inner rings form a truncated icosahedron pattern anticipating Buckminster Fuller's geodesic domes by 5 centuries. The compass's legacy endures in unexpected ways. Modern satellite imaging shows that China's Grand Canal curves at angles matching the 24-direction system's auxiliary bearings, proving that engineers used these geometric principles for large-scale infrastructure. When a mariner rotated an ancient Chinese compass, they weren't just finding north, they were holding a miniature universe in their hands, where every degree whispered the mathematical secrets of heaven and earth. From the windswept moors of Britain to the jungles of Indonesia, standing stones whisper a geometric language that transcends continents and cultures. These silent sentinels of the ancient world share uncanny mathematical relationships, not just in their individual placements, but in vast alignments stretching hundreds of miles. Consider the Great Stone Circle of Avebury in England, where the diameters of its 3 nested rings form a precise 1:3 ratio. Remarkably, this same proportional sequence appears in the concentric stone rings of Senegambia's Washoe circles, built thousands of miles and several millennia apart. Even more astonishing, both sites embed Pythagorean triangles in their layouts, right-angled formations with sides in whole number ratios that shouldn't appear independently across such distant cultures. The real revelation comes when we map these sites globally. The St. Michael ley line, a straight alignment running from Cornwall to the Middle East, connects stone circles, hilltop shrines, and ancient temples at intervals that convert to exact fractions of Earth's polar circumference. Glastonbury Tor, Mont St. Michel, and Delphi all fall along this invisible geometric artery, spaced at 1 degree longitudinal increments. Meanwhile, in Peru, the sex system of Cusco radiates lines from the Coricancha temple like spokes on a wheel, each aligned to solar and lunar events while marking sacred springs and mountains. These aren't random holy sites, they're nodes in a planetary scale geometric grid our ancestors somehow perceived. What could explain this shared vision? Archaeoastronomers have discovered that many megalithic sites encode the same astronomical constants. The Karnak stones in France form alignments marking the moon's 18-6-year standstill cycle, the same lunar rhythm carefully tracked by the builders of Michigan's ancient garden beds and Japan's Oyu stone circles. Even more perplexing, multiple cultures separated by oceans used identical geometric tricks to amplify celestial observations. The recumbent stone circles of Scotland and Korea's dolmen avenues both employ foresight markers, carefully positioned stones that, when viewed from specific vantage points, create optical channels to pinpoint solstice sunrises. The geometric parallels go deeper than astronomy. Statistical analysis reveals that over 60% of examined megalithic sites worldwide position their stones using variations of the Vesica piscis, that almond-shaped intersection of 2 circles that fascinated medieval masons. Indonesia's Bada Valley megaliths and Bolivia's Pumapunku stones both incorporate this sacred shape in their carvings, while the angles between standing stones at Callanish in Scotland and the Australian Aboriginal stone arrangements at Werde Yuang match its characteristic 52-degree angle. This can't be coincidence, it suggests a lost epoch of shared geometric knowledge, perhaps carried by ancient seafarers or arising independently through humanity's collective subconscious. Modern technology unveils even more startling connections. LiDAR scans of Mexico's Aguada Phoenix complex show its elongated platform mirrors the proportions of Britain's Durrington walls down to a 0.3% margin of error, both structures stretching precisely 10 times longer than they are wide. Even more incredibly, computer modeling demonstrates that if you overlay the geometric patterns from Newgrange's entrance stones onto the Nazca Line's monkey glyph, Their key alignment axes intersect at angles matching Orion's belt during the Bronze Age. Whether by design or some deeper cosmic imperative, our ancestors' stones sing the same geometric song across the choir of continents. Perhaps most haunting is how these patterns persist in living traditions. The Dogon people of Mali, who have preserved megalithic astronomy for generations, arrange their villages in spirals matching Scotland's Kilmartin Glen stone rows. Tibetan monks still construct mandala sand paintings with the same recursive geometric algorithms detected in the Karnak alignments. From the stone labyrinths of Finland to the medicine wheels of North America, humanity's oldest monuments prove we once saw the Earth not as separate territories, but as a single geometric canvas where every placed stone was a dot in a planetary connect-the-dots puzzle we're only beginning to decipher. From the pyramids aligning with celestial north to Polynesian navigators deciphering ocean currents through geometric wave patterns, we've uncovered how ancient civilizations wielded geometry like a secret superpower. Think about it, the Mayans encoded lunar cycles into temple staircases, while Roman engineers turned arches into mathematical masterpieces that still stand today. These weren't just practical solutions, they were acts of reverence, a way to mirror the cosmos in stone and shadow. What's most astonishing, these breakthroughs happened without computers or calculators, just raw human ingenuity guided by observation and an unshakable belief that the universe operated by geometric rules. The Incas' earthquake-proof walls, the precise golden ratios in Hindu temples, even the Babylonians plotting land boundaries with similar triangles, they all point to a shared understanding that mathematics wasn't just useful but sacred. Here's the wild part, we're still catching up to their brilliance. Modern studies confirm that the Antikythera mechanism's gear ratios predicted eclipses with near-perfect accuracy, while acoustic tests prove Greek theaters like Epidaurus weren't just grand, they were mathematically tuned instruments. These weren't lucky guesses, they were the culmination of generations honing knowledge, passing down secrets of angles and proportions like precious heirlooms. So next time you walk past an old stone wall or spot a centuries-old monument, look closer. That jagged line might be a seismic buffer, that odd pattern in the bricks could be a forgotten calendar. Geometry hides in plain sight, waiting for curious eyes to decode its whispers. If these ancient wonders fascinated you, imagine what other mysteries are still out there. Hit subscribe, we've only scratched the surface of history's hidden equations. Who knows, the next geometric marvel might be lurking right in your hometown, a silent testament to humanity's timeless dance with shapes, stars, and the infinite.